Hello, my name is Peter Mendham. I'm CEO of Bright Ascension, and I'm going to take the next 20 or so minutes to talk to you about our approach to supporting flight software development for high volume applications. So to kick things off, I'll give you a bit of background about who we are and where our approach has come from. We're a specialist space software company based in Scotland, and we've been offering a range of software products and services for the last 10 years. We saw our first mission that we supported launch in 2014, and now there's 29 spacecraft that are between 3 kilograms and 50 kilograms, so from CubeSats up to on small sats using our flight software. The majority of those are also using our mission control software, and that's across a wide range of applications, everything from Earth observation through to communications. Most of the customers that we're working with, including many of those due to launch this year, are looking at constellations. Either they are filling out constellations or they are piloting them, or some form of multi-satellite mission, which is the springboard for today's talk. And we're working with customers across the world and 6 continents. As well as that, we collaborate with lots of different industry players, from organizations, commercial organizations, through to agencies in a variety of R&D activities and standardization activities and things like that. So that has been our starting point for encountering what I'm calling here the high volume problem, which is looking at applications that involve a large number of satellites. And that can either be as a constellation or as part, or something looser, part of an overall program. But in both these cases, the satellites need to be coordinated to deliver the service that we're really interested in. I'm using service very broadly in this case to mean something commercial, something scientific, whatever the overall need is. So in most of the cases that we're working with, the satellites tend to be on the smaller end, so nanosatellites particularly, and these will need to be replenished as part of the normal operation of the service. And so that means new satellites, typically with new hardware capabilities or built by new satellite integrators, are being brought into the constellation or service, and those will also have new software associated with them. The satellites that are flying will also see updates, both through maintenance and adding new capabilities. And between both of these, this is leading to a situation where you have a highly heterogeneous constellation or system, and the system is very dynamic because parts of it are changing. But at the end of the day, the whole thing has to be managed as a whole. To kind of summarize the various aspects of the problem that we have then, is that we need to be able to support applications where software is available as soon as possible, to support early integration, to support testing, operations development. And software, once it is integrated into the system, needs to remain flexible as requirements change, as the service adapts and things like that. At any stage, software needs to be able to be changed or to be integrated very quickly, and typically with a large amount of functionality. Increasingly, functionality is being shifted from hardware into software to make use of the flexibility and speed that the software development is giving us, but that adds extra complexity to the system. Despite all of this, the software needs to be reliable. It's a mission-critical part of the system, and it needs to be able to scale across the whole flight ground system to be able to form something that's complete. And that flight ground system is very diverse. It has dissimilar elements throughout it. And despite all of that, we need the whole system to be operable. The effectiveness of our space system depends on how easily we can operate it to achieve our service and mission goals. Our answer to this has been in the form of Generation 1, which is a technology we've been developing for the last 10 years. And I'm going to tell you a bit about that today, take you through it, show you where it's come from and how we're using it to address the high volume problem, and then look at it in the context of a couple of case studies and show you the bits that are working, the bits that aren't working, and how we're looking to address some of those in the future. So the generation one has three aspects to it. It's model-based, which it means it captures a machine comprehensible version of the software architecture, which can be used by tools and other aspects of the overall workflow and system. It's based on software components, which gives us a unit of reuse, and those are held in libraries along with their tests and documentation. It's service-oriented, which means that all of the different parts of the system, the different software components, interact with each other in terms of well-defined services. And this has many positive impacts on the way the system is constructed and used, including positively impacting operability. So these different things mean that generation one at its core is a meta model. It's a language independent set of service and protocol definitions, and it's a set of tools and a framework. And then we add on to that sets of component libraries to create development kits based on generation one, and those can then be applied to both flight and ground software. So a starting point for generation one is the need to reuse software. So in order to address challenges of being able to create software quickly and for a diverse system, which is very prone to change, so it's very dynamic, there is one way of tackling this is to be able to reuse software. And if the differences in this software is not visible at a high level, it becomes a real challenge to manage when we look at large scale systems. So when we look at high volume development, managing change across that development can be very difficult if the differences between the systems that are evolving are buried down in source code. We find that it's better to be able to reflect a lot of the differences at an architectural level. And so this becomes a critical factor in the size of the units of software that we are choosing to reuse. And what those affect is how flexible and adaptable the reuse is, how visible it is, and how we can manage the overall reuse, and also the impact on the overall development process. Now, obviously, there's a sliding scale here. It's a spectrum, but just to take 3 points along that scale, if we look at one extreme, we look at very, very large units of reuse. So this is where we basically reuse like a whole piece of flight software or very large flight software applications, and we do not change these. So this either is the same or it isn't. And if it isn't the same, we treat it as something completely different. So in this case, the amount of flexibility we have from this software is very limited. And so we would need to end up adapting mission and payload concept of operations to the software that we have. And this often moves some of the need for flexibility from the flight software onto the ground. So the process here is really simple because we're just grabbing an application. Couldn't be easier, but it does give us a lack of flexibility, and the complexity hasn't been solved. It's just been moved. If we take a kind of medium point and we're looking at sort of library level reuse, or we're looking at quite small applications of which we're going to have a number, this helps us achieve a compromise. We have some flexibility. We can pick and choose libraries, and the process itself is quite easy to manage manually. The number of libraries that we're working with is probably quite it's just a few, so it's relatively easy to manage at a human level, but it does limit the amount of flexibility that we have. If we go to the other extreme, or almost the other extreme, if we look at very relatively small units of reuse, then we can achieve a very high level of flexibility. If we allow these to be encapsulated and to be configured for a wide range of applications, then it allows us to reflect the differences between systems in the units of reuse that we choose and how we configure them, as opposed to needing to modify those on a regular basis. The challenge here is that this makes the overall development process quite difficult unless you have good tools. So, you know, never wanting to take the easy route, that's the approach that we've taken. And these are what we call software components. So the managing of these units of reuse as software components means that they need well-defined and well-structured interfaces. So as part of generation one, we define what a software component is and what its interface defines. And that's two things. It's what the component provides the rest of the system, and it's what the component requires, what it needs in order to work. Both of those are captured as part of the component interface. So the high-level interface to a component is typically composed of things that you can, for example, see from ground. So things like what we would call actions, so commands, and what we would call parameters. So like telemetry parameters, read-only, or even configuration parameters, read-write parameters. Where components interact with other components, this is done using what we call services. And these are very clearly defined, and service connections can be made either statically at build time or dynamically at runtime. So these services describe these interactions between components, and this is completely independent of location. So it could be components that are like next to each other within a given process, or it could include components that are in flight or on the ground. So the flight-ground interface is actually defined in terms of services, and services describe behavior at a fairly high semantic level. What they do not capture is the encoding. So they don't define packets or messages or any kind of bit encoding, and that's very deliberate. They're completely independent of that. So where those services are within a process, they actually end up resolving to a very simple function call. So they are basically zero overhead. And then out of process, they can be mapped onto a protocol, and there is completely a wide open choice as to what you want to map that onto. So that allows us to separate the decisions about the semantics and what we're trying to represent from how it's being represented. And so that means that we can abstract the operation of the system away from messages, packets, hardware, things like that, and offer standard ways of working across a diverse, large scale and high volume system. All of this is great, but it means that there's a lot of information to manage. And if we were to handcraft flight software to be able to configure all of these things, to define services, it would either get very inefficient or just downright tedious. And I think that everyone will agree that tediousness in software will frequently lead to errors and mistakes of the kind that we really should be avoiding. So the best way to manage this is to allow tooling to help out. So to allow tooling to help out, the information that we need needs to be captured in a form that the tooling can help. And so that means that the information can be available to support the overall workflow. And things like when we're creating component types, to be able to add those to our libraries, then what code is necessary and what is necessary to implement is going to depend on the definitions of services. And the services provided by components also define things like the space-ground interface, as I was mentioning. So there's strong interactions between information and workflow that the tooling needs to support. So this information we then capture in the machine readable form that is our underlying model. And the aim of that is to allow it to be used by tools to speed up the development flow, to increase developer efficiency, reduce the scope for errors by removing tediousness, to be able to very clearly define the configuration of a system, and also importantly to maintain documentation, and documentation at an appropriate level, not just low-level documentation, but quite high-level documentation as well, and to be able to relate that to the overall system. So our model, so the models that you use in Generation 1, according to the Gen 1 meta model, are focused on capturing the functional architecture of the software system. And we capture that functional architecture in terms of these things that we call components, and also in terms of the interactions or the functionality that they provide, which is services. And so this considers the complete system. The model covers not just the flight software, or and not just the flight software on a single spacecraft, but it considers multiple spacecraft. And it also considers ground systems. So the tooling that works with this has the benefit of being able to see the larger picture. And this can be used across the complete development lifecycle. So we can start out with a model which is quite sketchy and just defines a few things at quite a high level, and then it can progress through development through to operations. And having a single source of truth for these things means that we can easily support interactions between different teams, particularly those involved in flight software development and operations. A side effect of the way that we're capturing this information in the model and the fact that we use types in a very strong way means that it's easy for tooling to determine the similarities and differences in different parts of the system and to be able to identify where those change over time. So where you have, say, constellations with different generations of spacecraft and different capabilities, the capabilities which are in common and different between those different generations of spacecraft can be identified from the model. Alongside the machine readable part, we capture human readable descriptions, and those can be used for documentation generation. So to kind of bring this all together, hopefully into a fairly concrete way, the overall workflow works by, well, I'll take you through an example of this. We could start out by defining a new component type, and that the aim there is to encapsulate some new functionality. We can specify the interface to this in terms of what it provides to the world and what it requires in order to be able to deliver that. And that type definition is captured in the model to do with, together with human readable information about that. We can then use the tooling to generate a skeleton, which we can implement, and that gives us an executable component type to be used on a system. And if we were using the model on its own, we wouldn't necessarily need to implement it. We could just use the model to represent functionality that maybe already exists elsewhere. Using these component types that we have implemented, we can actually define a complete software system by instantiating the component types to get components and connecting them together and configuring them. And all of the description of everything to do with that, including its configuration, is then captured in the model so that the tooling can get access to it. We can then run the tooling to allow us to generate and build and then deploy our software image. And that makes use of code generation to fill in all of the bits there to glue the components together. We can also generate documentation for different target audiences like engineers and operators based on the information that's captured in the model. We can also import that model straight into operations software, which means that the operation software can be immediately configured to talk to the flight system, and it understands, if you like, everything about the functional interface to the flight system at quite a high semantic level because of these services. And so this allows us to iterate very quickly and manage change in even a very dynamic system. So once we have all of that, we can then define operations in terms of the services that are provided by the flight software. So to bring this back to the original high volume problem that I was posing at the beginning, so the component-based approach really helps with reusing existing software. So using existing libraries, we can put together a starting point very quickly, and being able to substitute very small units of software in and out, that gives us a lot of flexibility in being able to adapt to change. The way the tooling works in terms of supporting the development flow allows very rapid development, and particularly it supports iterative development. And there's no restriction here in terms of the capability that we can offer. And the service-oriented approach and representing functionality as services gives us a way to manage the complexity associated with a very capable system. The reuse at a modular level, at a component level, gives us a way of managing flight-proven code with heritage, along with its associated tests at quite a fine-grained level. And so that allows us to gain a high degree of confidence in the code bases that we're working with. This scales through the model to very large-scale systems and also large-scale systems over time, so programs of satellites and high-volume manufacturing. And the model representation of all of this does help us manage the diversity, being able to see similarity and dissimilarity. The high-level services tackle this core problem of operational effectiveness of the system and the well-defined semantics of the services, and the fact that they are abstracted from the underlying hardware of the system gives us a very good starting point for operations automation. So I'll take you through a couple of examples now. The KLEOS constellation, so KLEOS Space is an RF reconnaissance data as a service company, and they are deploying an RF remote sensing constellation. The constellation is structured as multiple clusters of 4 satellites. So each satellite is a 6U CubeSat. And because it's being developed over time and new capabilities are being integrated all the time, then each cluster so far, and probably for the future as well, is different. So there are different capabilities within a cluster. Or each cluster has different capabilities, and it's quite likely that individual spacecraft within future clusters may also have different capabilities. But still, we need to operate this whole constellation as a service. So the recent clusters of the KLEOS constellation are using Generation 1 flight software, and mission operations for the whole constellation uses Generation 1 on the ground. And so the opportunity here, and the reason that it's being employed, is to be able to use the advantages of the model-based approach and the service-oriented approach that I've been talking about to help manage some of the complexity and similarity and dissimilarity in the system. And the component-based development has really helped with the ability to develop flight software rapidly for each new cluster within the system, where we are typically looking at development times for new clusters on the order of 2 to 3 months. So another example that is quite different, I think, to the KLEOS constellation is the FARADAY service. So In-Space Missions has a hosted payload service, which will have frequent scheduled flights. The first of the constellation is in flight at the moment, and there are further flights scheduled. And the aim is to provide a very rapid time to flight for new payloads. So a lot of effort has gone into creating a flexible and scalable hardware architecture. And so the software architecture has been designed to also match that, and is making use of the component-based approach of Generation 1. So every satellite is different. And so although the platform is similar between them and is shared between multiple payloads, the combination of payloads for each satellite will be unique. And some customers also have payloads on multiple satellites, which they may want to manage as a pair or set. And so that means that overall, the spacecraft need to be managed both individually and as a constellation. So the Generation 1 approach is being used for both flight and operation software, and the component-based modularity has been really critical to managing the diversity. And the services also have been critical in helping to define things like the standard payload interface, which allows us to do very fast track onboarding of payloads. And the model helps us manage this very diverse system of similar and dissimilar spacecraft. So to draw those use cases together, so over the 10 years and 30+ missions that we have been involved in, we have been able to increase the availability of these systems through the use of component services and model capabilities. And the main things that we've learned across that has been fed back into the definition of Generation 1. So this will seem like a circular argument, because Generation 1 has evolved to have the characteristics it does because of us identifying what works and what doesn't. So things like the finely granular reuse through components, the model-based approach, the semantic services decoupled from the underlying implementation have all been really important to success on the missions that we've been working with. As we've moved up to support these large-scale systems, we have found areas where the current definitions of things like, well, especially the model and service definitions have not quite kept up with the challenge of some of the high volume situations that we have found ourselves in recently, particularly around configuration management, where we're 70 or 80% of the way there, but the expressiveness of our meta model is not quite sufficient to capture everything that we need. And that has also been an issue with managing the evolution of the system over time. The services that we have been working with have been really powerful, but sometimes, again, we've hit limitations in what we can express in a service. And so these are the main areas that we've been working on recently in terms of extending the overall system to be able to support constellations and other very large scale systems with a key application area of high volume situations. So thank you very much for listening. It's been great to share that with you. And if anyone has any questions, I'd be really happy to answer them.